Hi, my name is Matan Broner. I'm going to be presenting Appraisal AI, a project that me and my teammates worked on, Fernando Guerra and Haoyu Zhu, as part of CSE240 Artificial Intelligence at UC Santa Cruz. So a little bit about our problem. What are we trying to solve? It's no secret that real estate price prediction is a really tough subject. It's almost considered an art. So we were looking to see if, given an image and just a little bit about information about the house, could you accurately predict the house's sale price? So as with any artificial intelligence problem, the data is where you have to start. So we had about 15,000 rows. Each of them is a home, with each row consisting of an address, a number of rooms, city, listed price, and a front-facing image of the house. We have an example row here. We did a few data preprocessing techniques as listed here. I'm going to be going into each of them in a little bit more detail. So we found out early on that the rows in our data set were not consistent. We had a lot of rows which linked to images that just weren't satisfactory, and so we combed through each image as a group and decided which ones were satisfactory for our problem and tossed about 3,500 rows. We also resized images using OpenCV to about 128 by 128 pixels in order to be able to use them in a CNN. We combined columns, meaning we took the ones that were highly correlated, such as beds and baths, and created a rooms column in order to increase the correlation with sale price. We also use min-max scaling on the prices in order to allow for regression, so that means taking all prices and moving them to a 0 to 1 scale. We did the same with the rest of the continuous columns, actually using sklearn's min-max scaler, but the same idea of a 0 to 1 scale. We also then use a zip binarizer to encode the zip codes into a sparse matrix so that they can actually be used rather than their literal values, which don't actually mean anything in the case of this model. And so a little bit about our model itself. We used a 2-branch model with a concatenation layer. So as you can see here, this is the CNN. We used 3 conv blocks with filters ranging from 32 to 256 and 2 fully connected layers at the end. We also use a multi-layer perceptron with a little bit of a simpler design of 4 fully connected layers with an hourglass shape in order to be able to learn fine-grained details while still allowing for compression towards the regression. And the concatenated model, which uses another set of fully connected layers to compress data before the regression, but uses the 2 branches themselves as input. And we used the Atom optimizer with a 32 batch size and the learning rate shown here. Finally, we use grid search. We use the HyperOS library, which is a HyperOpt implementation using Keras, and we optimized using grid search for each of the 2 branches, and finally optimized the concatenated model itself. And this was inspired by the EfficientNet paper, which uses grid search to optimize. So a little bit about how we did. As you can see, here's the losses for each of the branches. The CNN is a little bit more fluctuating, but at the end consistent, and the MLP is shown to the right. Here is a concatenated learning. As you can see, we did pretty well with an average loss of about $121,000. There's a little bit of spikes in the training loss, which implies a little bit of overfitting, but overall we did fairly well. And so about the future, what we're looking to do, we are looking to use some K-forest regression techniques, which have proven useful in similar tasks. We're looking to reduce overfitting in the concatenated model. Perhaps there's some cloning of certain rows. And finally, we're looking to create a model that can mimic the process of generating tabular data for each image so that in the end we can just use images for price prediction, which would seem a whole lot more useful. Thank you for watching our presentation. Hopefully you learned something from it, and goodbye.